This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Welcome to Software Engineering Radio. I'm your host, Gavin Henry, and today my guest is José Valim. José Valim is the creator of the Elixir programming language and, I love this title, Chief Adoption Officer at Dashbit, a company that focuses on sustainable open source and continuous adoption to boost the Elixir ecosystem. He's also a seasoned speaker and author of 3 programming books and an active member of the open source community. José, welcome to Software Engineering Radio. Is there anything I missed that you'd like to add?
No, I think that was a good intro, and thanks for having me.
Thank you. Perfect. We're going to have a chat about what Elixir looks like today, the challenges you faced at the time you decided to create Elixir, what Livebook is, and finally, Elixir joining the machine learning world. So I like to always ask, when we're speaking to someone that's got major achievements like you, what challenges were you facing at the time when you thought, you know what, I'm going to go and build something versus I'll try and fix what I'm working with at the moment? What challenges can you remember you were facing when you decided to create Elixir?
I'll answer the second part of the question, which is, why I decided to create something instead of fixing it. And I hope I'll come back to the first part of the question. But to me, I like to say that most people, when they have a problem, they don't necessarily think that they will, I'll create a new programming language. That's definitely going to solve my problems, right? It's like the regular expression meme, right? You have a problem, you use regular expression, and I will have 2 problems. And creating a programming language is definitely going to bring way more problems than 2. So when I started, I was interested in learning. I had issues like writing. I was struggling to write concurrent software in languages like Ruby. And then I say, okay, if concurrency, this was 13 years ago, 2010, 2009. And then we're starting to hear a lot about concurrency, right? And today you have 4 cores on your wristwatch. So you're starting to hear a lot about concurrency and people saying concurrency is going to be the future. So I was like, well, if concurrency is going to be the future, I really want to learn and figure out how I write concurrent software. And then I started on this journey of learning and thinking I would learn ideas that I could bring back to Ruby, for example. But throughout this process, like I say, there are points of no return, there were things that I learned. So when I learned about functional programming, because a lot of the issues I had with Ruby at the time is that, for example, if you had 2 threads and they were trying to change the same place in memory, that place would get corrupted. And in functional programming, we are not changing things in place. We are always transforming them. And that really resonated with me because I thought, well, that's a better programming model, because I don't have to track how things change over time. And it also solves the concurrency issues. So it was a point where I was like, okay, I think in the future, when I write software, I want to write software that is functional, or if not functional, where things are mostly immutable by default, where I am transforming things. I don't want to mutate things anymore. I definitely want to mutate things, but not as my default way of building systems. Yeah, and then the other point was where I learned about the Erlang virtual machine. And then I was like, well, this is at the time. So going back to 2010, if you look at all the programming languages that were coming out at the time, they were all talking about concurrency. You're like, Go had a focus on concurrency. Swift came later, had a focus on concurrency. Clojure had a focus on concurrency. So concurrency was certainly a big topic. And the thing about the Erlang virtual machine was not only that they did concurrency, but they did it 3 decades ago. And they also solved the next step, which is if you're writing a system where a machine is not enough to power that system, you need to use multiple machines. The next step is that you need to think about distribution and how all those machines, they are going to work together to tackle a certain problem. And then I was like, well, the Erlang virtual machine not only solved the concurrency, but they solved the next problem, which is distribution. And I fell completely in love with it. And I was like, this is what I want to use. So at some point in this, I just want to learn. Just by learning, I completely changed my career in the sense that I was like, this is the software that I want to write. This is how I want to write it. And the more I used the Erlang virtual machine, I thought that there were new ideas that could be explored. And I thought that the most productive way to start this conversation of like, how can we expose or use the Erlang virtual machine in different ways was by creating a new programming language. And that led us to where we are.
Wow. I mean, I suppose it's a great way to follow something that you get excited about. I was reading an article by Paul Graham the other day, which he just released, called Do Great Work. And I think the main takeaway theme from that is, follow what's exciting you, because that's going to keep you driven and keep you interested.
Yeah, and I think it ties in with the challenges question, because definitely I had a lot of challenges. But I think because of like I was excited about it, I never really saw that as like a challenge in a way, like you can consider challenge in a way that it can even be crippling or something that would be too hard to overcome. I always saw it. It's like, I'm excited about this and there is work to be done. There is always work to be done. So let's do the work. And, in a step after the next step, we will eventually get somewhere. And I always had this idea that, it could not work at all. Right. So I was not necessarily too worried about failing. I always had the concept like, well, it can fail. I can spend like 3 years of my life and working on this and it's not going to go anywhere. And I always had in my mind that that's fine. It's not a problem. I'll definitely have learned a ton. I would have enjoyed the whole process. So that's fine.
Yeah, you always learn something. Could you just take a step back and define the Erlang beam for us?
Oh, so the Erlang virtual machine is, well, the same way that we have the Java virtual machine and the Java programming language, we have the Erlang virtual machine and the Erlang programming language. And the Erlang virtual machine and the programming language, they were created by Axon, which is a telecommunication company. And they created it with the specific goal of to power their telecommunication system. So today we say, I hear like different percentages, but we hear like, like the majority, like more than 66% of the whole 4G traffic in Europe is going through Erlang machines. I hear people say it's like 66% of the global traffic and things like that. But the point is, Erlang plays a very big role in telecommunication today. And as I was saying, like to build those systems, they had to tackle a bunch of different problems related to concurrency, distribution, fault tolerance. And that's one of the other things that made me fall in love with it because, like many of the design decisions behind Erlang and the language, they were all driven from like an engineering principle. It's like, well, we have this problem and how we are going to solve this problem, right? Like they did not say, look, we want Erlang to be functional, for example. Right? They did not start with the features and then they derived the language from it. They're like, well, we have those problems. Oh, we need concurrency. We need this idea of supervisors for fault tolerance. And they were building everything from those principles. So one of the reasons why immutability is important from the point of view of Erlang is because, so if you have concurrency, if you have many things running at the same time, and if now those different entities, they share a state because you have something that is mutable, it's shared. If one of those entities crash, right, can you guarantee that when it crashed, it did not crash in a way that the state was corrupted? And therefore, other things that depend on that same state are now corrupted too, or they will now be depending on this mutable shared thing that can break the system. So they're like, well, we don't want to share a state because if ever guarantee that everything is isolated, it's easier to restart things. And therefore, it's easier to have a system that can heal itself and be fault tolerant. So, when you are starting Erlang and its wisdoms, like there are a lot of, interesting design decisions and why they were done, which is why I really enjoy working with it.
I'd never actually made the connection between immutable state and the supervisors or, crash early and often, because it doesn't matter if you crash because the data has not been changed. I've just kind of realized that. That's a really good point. Since you are, I just love saying this, the chief adoption officer, if I was to chat to someone new, to Elixir or yourself, we're chatting to someone new, what would be the top 3 things you recommend that I tell them to make them want to get excited and jump in? Like your elevator pitch, as it were.
That's something that I am currently rethinking. And I guess we're going to jump into it. So for years, like literally, I think since 2014 or 2015, so 8, potentially 9 years, I had like this go-to talk about why Elixir, which is called Idioms for Building Distributed Fault-Tolerant Applications. If you Google that, you're going to find versions of this talk. You'll be able to see how I aged through time because I've given it so many times. Every time I go to a non-Elixir event, that's the talk I give. And the talk is mostly, like the elevator pitch is mostly, well, it's the Erlang virtual machine, right? Like it's the problems about concurrency that we face today, how to write, maintainable software. And now I am working on a new talk where Livebook is going to be the core of the talk and use that as a driving point to show everything that you can do with Elixir. Because one of the things that I think like my previous talk, it always resonated well with, maybe it's a consequence of the events I was usually invited to, but it always resonated well with senior developers, right? So it's like, well, like this idea of thinking about concurrency, how you can speed up your tools, how you can reason about failures. Like sometimes it's going to make sense once you have like let's say the battle scars, right? Like after you have spent like hours of your night not sleeping, but trying to understand why a system is failing. So I think like that talk like can resonate really well after you have some experience and you went through some of the pains and you want to rethink how you design and approach systems. But now that we are like with Elixir, with Livebook, now we have really a great platform for to start exploring and twinkling with ideas. And we're starting to have like visual tools as well that are really accessible. Like, you are in your Livebook.
That resonates completely with my journey because I'm senior as well. And all the pain points are solved in the way that you just described. How you can run code snippets from the documentation. You can jump onto the IEX interactive thing to just run your own code or connect to a live deployment of Elixir and connect to the Beam and run the same functions that connect to the same database. All these things that you tried to figure out before when you were younger and solve all these problems. It's just, I think it's not luck, but it's all just come together at the right time when everything's kicking off on that type of ecosystem. Anyway, when people see Livebook, if they haven't as well, that is just mind-blowing as well. So let's move on to Livebook. So what is Livebook?
So Livebook is a computational notebook platform. And that's a fancy way of saying, well, think if you have like your IDE and a web browser and like a interactive shell all integrated into a single place. So you have places where you can write some code and then you can execute it immediately. We call those places cells. So we can execute a code cell immediately, get the result. But because it's running in the browser, you can actually get your Elixir code like plotting a chart or playing some audio and doing all kinds of interesting things we're going to explore. And at the same time, you can write like some prose, some text, some markdown documentation. So it's this idea of code, documentation, and a rich environment all in one place. And that opens up like a lot of possibilities of things that you can do, build, and explore. That's it in a nutshell.
And is that different from something like CodePen or one of these places where you could run, or like the Gopher playground for Go, where you can run specific code? It's much more than that, isn't it?
Yeah, so for those who are familiar with Jupyter Notebooks, it's something, it's closer to Jupyter Notebooks, but it's not only a playground, because the playground, you think like, well, it's a single place, right? And then I change, I evaluate, I get the result, but you're not really writing a document, you're not really writing a story, a tutorial, an application. It's meant to be like a scratch pad. It's something that you're going to throw out. But with Livebook, it's not necessarily meant to throw out. Of course, you can explore ideas and discard them, but we use that for documentation, writing applications, and building things that are meant to be long-lived.
And it's a standalone application that you can either connect to on livebook.dev or run it yourself on your own desktop or through Docker or deploy it like a normal web app. Is that right?
Yeah, exactly. It's a web app. It's implemented as a web app, but we know we have like Livebook desktop. So you just run that, we package that and you can run that in your machine. But at the end of the day, it's a web app. It's open source. So as any other web app, there are many different things you could do with it.
Cool. Why was it created?
Well, so the story of why it was created, it's related to machine learning. So I'll try to make it very short, but we started as a fork for machine learning, and we can talk about why we started that. And because Jupyter Notebooks, and the biggest ecosystem for machine learning is the Python community. And we know that, Jupyter Notebooks, they play a very important role in the machine learning community for Python. So at the beginning, it was really like, well, what if we want to do machine learning in Elixir and Jupyter is important? What if we have like the equivalent of Jupyter for Elixir? So we thought that, as part of a machine learning journey, I was like, well, this is going to be a required stop. So we have to tackle it. And one of the things that we could do is that, so in Jupyter, which comes from Python, you can actually plug different languages. I was like, from the beginning, say, I wanted to roll our own. And that's for two reasons. So one of the reasons is that Elixir is good for web, for writing web applications. And a couple of years ago, we announced like LiveView, which is a way of building like rich interactive applications without necessarily having to write JavaScript, but it's all interactive and reactive, and you can build like really modern fancy applications powered by Elixir. And I was like, well, we have the tooling, right, to build this. This is what Elixir is.
And LiveView is part of the Phoenix web framework project that is written in Elixir, isn't it?
Yes, correct. So I was like, we have the tooling. And if you looked like at how people are trying to improve Jupyter Notebook, so there are a bunch of like commercial versions of Jupyter and so on, and they're trying to add features like collaboration. So for example, collaboration is something that is very easy to do with Phoenix, right? Because it was designed with this real-time interactive aspect in mind. And then I was like, okay, like that's a problem they currently have, and it's a problem that we can solve. And then the other thing was that one of the main issues that people have with Jupyter Notebooks is that they're not easy to reproduce. And there is a whole other conversation that we can have on this. But in a nutshell, it's like if you have, imagine that in one cell, so imagine having one place, say x equals 1. And then in the next cell, like the next code that are going to evolve is like x is equals x plus 1. In a Jupyter Notebook, it means every time you execute the second cell, the value of x is going to increment. Because the way that Jupyter Notebooks work is that you're working against like this state that is alongside the notebook. And the problem with that is that imagine that you create a recipe, right? And you send to somebody. If somebody executes it from top to bottom, you're going to be like x equals 1 and x equals x plus 1, right? So, and then you can say, oh, the result at the end was 2. But if you give it somebody else and they decided to execute the last cell 2 times, x is going to be 3. So it means that every time somebody executes that notebook, they may get a different result. And then we're thinking, well, this is because of mutability. Elixir is immutable, like it's immutable by default. So we should not have those problems. And if we do not have those problems, we can rethink how we are going to approach the notebook. So this is something I think, telling the story now, it's something like, it's a very different compared to Elixir, because with Elixir, I was like, I want to explore, I want to learn. I don't necessarily want to create something new. And with Livebook, from the very beginning, it was clear that it was worth to create something new because the differences are so many that it's worth exploring that new direction. And it's like we're going to get a new tree, and once we shake it, a bunch of interesting things are going to fall off. And we were excited about exploring that. So that's kind of how we started with Livebook. And at the beginning, like, I would not be able to describe like 20% of the features that Livebook has today, but that was the idea, right? We knew like if we plant this seed, is like interesting things are going to happen, and we decided to do it.
Just to revisit the immutability thing there, because x was assigned a value at the start of your recipe, you would need to take that and assign it to a new value to change it, because x will always be the same. That's the point there, isn't it?
So yes and no. So in Elixir, that's something that it often can be confusing. In Elixir, the values, they are immutable. So if you think of a value, it's something that is in memory. And the thing that is in memory is immutable, but the values you can change to where the variable is going to point to. So in Elixir, I can say list is equal a list with 1, 2, 3. And then I can say list is equal 4, 5, 6. I'm just changing to where the variable points. And this is a transformation that only happens in the program. But when it comes to the memory, nothing's being changed or manipulated in memory. So the difference between Python and Elixir here is that Python, when you change X, it changes every time you change X. You can think like each cell, it gets all the state in the notebook, and then it changes these things and it dumps somewhere. So for every time you do X plus 1, it goes to this global place and say, hey, what is the value of X? And then say, oh, it's 2. Let's increment 1, it's 3. And it puts again back in this global place, where in Elixir, everything is linear. So if the value of X before you execute a piece of code was 1, at the end, the value can be 2. But if you execute that piece of code again, we don't get the value from like this global place that is shared. We just go back to the value of X before the cell. So it's like a mathematical formula, right? So we have the inputs, we have the outputs. And in this case, the input to a cell is not going to change unless you change things before the cell. I don't know if I can explain if it makes sense. Yeah.
No, that's perfect, because that reinforces the view of when you're debugging immutable code, you know you don't have to try and figure out what that value changed to, because it's not going to change.
And I think like it's a good example, right? Which is like, if you're debugging code, if it was immutable, so imagine that you have X equals 1 and X equals X plus 1. If you put a debugging between those two lines, in Elixir, the value of X is always going to be 1, right? Because even if you change the value of X later, it's not going to affect the value of X before, right? And I think that's the difference, right? It's very linear.
Yeah, I think in some of the examples in books and documentation, that's when they usually introduce recursion, so they can show you how to increment a variable by returning a different value each time. Is that right?
So in Elixir, when we use recursion there are many reasons why we use recursion. So one of the ways that you can think about it is we have the data structures, and in order to traverse those data structures, you can use recursions. But when it comes to a state, so if you think like, well, in Elixir, if nothing is, I don't know if I can explain this for audio, but if nothing is mutable, if everything is immutable, right? Like, how do you create state? So imagine that somewhere in your web application, you want to store how many users are connected at the same time, right? So that thing needs to be shared state, because every time somewhere joins, you need to say, hey, I want to increment this by 1. Every time somebody leaves, you want to decrement, and you want to be able to increment or decrement this from anywhere you want, right? So it needs to be state, it needs to be shared somehow. In Elixir, the way you would achieve this is using recursion. So we create this idea of this thing like called processes, and those processes, they can send and receive messages. So what they do is that so a counter would work something like this. You have a function that you call it saying, we have a function called loop, and then you start with a value of 0. Loop is 0, which is your current counter. And then you're going to receive messages. If you receive the message of increment, you're going to call the same function, you're going to call the same loop function, but incrementing the state by 1. And if you receive a message of decrement, you're going to decrement 1 from the state, and you can receive a get message, and then when you receive a get message, you are going to send a message back to the person who sent you the message and say, hey, you wanted to get the value of the counter, here is the value back. So the discussion of recursion when we are thinking about immutability and mutability in Elixir is because we use recursion and message passing as the way to emulate state, right? So there is no mutable state per se. We have functions with their state, and then you can send message and back. But again, you're never really mutating the counter, right? Again, it's like never the X of value is like it's changing under your feet. You're just pointing to different things as you move forward.
Thank you. That was a perfect explanation. That helped me as well. So I hope it helps the listeners. So we'll just finish up the Livebook section with 2 more questions before we get into machine learning in general with Elixir. So Livebook was created because you want to be able to support machine learning and Elixir, and for a way for users, data scientists, programmers to explore data through Livebook. Is that correct?
Yes, that's how it started.
Okay, and this is just a question from me. How does it save the code you're working on? How does that work?
And that's also another, going back to the Jupyter conversation. So one of the positive and negative things about being widely adopted as Jupyter is that you have plenty of materials and plenty of experience of people saying, hey, this should have been done differently, or this needs to improve. And for us to get started, it means we can consume all this material as well and learn the lessons that Jupyter learned through time. And it's there documented for us to learn. And one of the things in Jupyter is that, so if you think of a notebook, if you think of a document, right, how it's going to be shared. Some things they are opaque, like, if you have a Word document or an Excel document and you try to open it like in an editor, it's just going to be like blobs, I think. Excel for sure. Maybe docs, depending one of the formats, not, but it's a blob. You can't do anything with it. And that was one of the things that people like a Jupyter notebook, you cannot open it in disk. And this has problems that, like doing a code review, for example, can be hard because you cannot just submit a change and have somebody review that. Today, there are tools in GitHub to improve that, but it's not plain text. And for us, we wanted to tackle this problem. So Livebook notebooks, they say that they are live markdown files. And it's a subset of markdown. We restrict a little bit the markdown that you have there. So it has a very specific structure. And that's it. So, you can open it up, you can review it on GitHub, drop some comments and all this kind of stuff.
Oh, excellent. So you could see your Elixir programming in the markdown document. Perfect. Okay, we're about halfway through now, so I'm going to move us on to all the exciting progress in the machine learning world for Elixir. So I've got another question here, which we're struggling to do at the moment. In your own words, what is machine learning?
Yeah, so one of the ways that I saw like machine learning, and I don't know if it's good, but one of the ways that, or if I'm recollecting properly, one of the ways that I saw it described is machine learning is about defining models to execute certain tasks that it would be impossible or very error prone for us to define or declare those tasks manually, right? So for example, think about a chess game. Like, sure, there are the rules of chess and we can describe, but imagine that you want to build a model that wins a chess game. It would be very hard for us to encode those rules in software, right? Like using conditionals or whatever, right? Oh, like, there are so many states, so many combinations. So the idea of machine learning is how can I define a model, something that I can train, that can learn from based on something, some data, some training set, and then execute that task for us without us explicitly describing or declaring what we wanted to do. I guess that's one possible interpretation.
Yeah, that's good enough for me. I mean, in Sean's book, he says exactly that. Once you get to a point where you're doing rules for some type of system and there's so many edge cases, that you then move to machine learning and either building a model or finding the right model. And he says the model, I'll put a link to the book for everyone in this. He says a model is just another name for the algorithm that you choose to crunch the data set, which is the NX data structure, which we'll get to, I think. Just to summarize, why is Elixir a suitable programming language for machine learning? I think we've touched upon it on the past half an hour or so.
Yeah, so interestingly, when I started with Elixir, Darling Virtual Machine was not necessarily a good candidate for machine learning. But if you look at machine learning in Python, for example, a lot of it's powered by libraries in C, C++, I think some in Fortran. So it's all native code. And so a lot of people say, like one of the merits in Python for machine learning, it's how Python can be such a good glue language between, the high level Python software and the low level code in C. And in the Erlang virtual machine, so there are things that we did not talk about, like so I kind of mentioned that we write our code that runs inside those processes that they send and receive messages. And we can kind of pierce together that those processes, they're all isolated. They don't share anything, right? They can only exchange messages and they are very cheap. They're very lightweight and we can run like millions of those at the same time. And the Erlang virtual machine, it's also preemptive, which means that those processes, it's not possible for one of those processes to starve the system, to do so much work that the rest of the system, it cannot respond because that thing is busy. And in order for this to happen, it's essential that, like if you have an infinite loop, for example, or if you have anything that it's very expensive, it's essential for that thing to, if it has to do a lot of work, for it to say, hey, I'm going to do some quota of work, and then I'm going to stop. And then the virtual machine will check if anything else like needs to do some work. And if something else needs to do work, those other things are going to do the work, and then you come back. So you are preempting, like everybody gets some amount of work, and then eventually everybody is going to get to the end of their journey, is going to finish the work that they have to do. And the issue with calling C code was that, well, if I just go and call a C code that is going to do like some very expensive 3D or 4D matrix multiplication, that thing could take a lot of time, and that can starve the rest of the system. So almost 10 years ago, in order for you to, if you wanted to integrate with native code in Erlang, you had to rewrite the native code. You had to write the native code to say, look, I'm going to do just some amount of work, and then I'm going to yield back to the Erlang virtual machine for it to see if something else needs to run, and then do a little bit more. So it had to do all this yielding. And of course, depending on the algorithms, like it may be hard, like to rewrite. Imagine if we had to rewrite all of the machine learning, like algorithms and computations to work based on those ideas. It would be a lot of work, a lot of time spent. So they introduced about 8-9 years ago this idea of called, so when you have to call C code in Erlang, we say it's a native implemented function. We call it NIF. So it's native code, low-level code, native implemented function. And they introduced this idea of dirty NIFs. And the idea of a dirty NIF is that you say if that dirty NIF is going to do a bunch of CPU work or if it's going to do a bunch of IO work. And we have separate threads that those threads can run, and you customize how many threads you want to have. So you give separate threads to run this dirty work, but that dirty work is not going to run together with your Elixir code. So it's running on a separate operating system thread. So they introduced this whole abstraction of dirty NIFs. And so basically they added this way of how we can now integrate native code into the Erlang virtual machine. And, once we had that, if you compare Elixir with Python, it's like, well, now we can integrate native code. So we can bring all those algorithms, those libraries for machine learning. That's exactly what we did. So for the machine learning in Elixir, it's not like we are starting from like all the low level from scratch. We are using Google XLA, which is an accelerated linear algebra library from Google, which Google uses for TensorFlow. It's the same library. We wrote bindings for that, and we build on top of that. We also have bindings for libtorch, which is what the PyTorch library from Facebook, right, another big player in machine learning, it's bindings to the low-level library that the PyTorch uses as well. So that's how we started with the machine learning. And it was mostly like, well, technically we can do it. And we talk about Sean Moriarty and his excellent machine learning book. And before he wrote the machine learning book, he wrote the Genetic Algorithms in Elixir book. I say like this is the book that changed my life, but I never read it. And the reason I say that is because as soon as that book was published, I think on the first or the day after, I sent an email to Sean. I was like, this is very exciting. I was always interested in having more machine learning stuff in Elixir. Let's build something together. And that's when we got, we can build something together. We can use the same native libraries that Python uses. And we started slowly building this whole infrastructure.
That wasn't out very long ago, was it? 2021, you published that book. I'll put it in the show notes as well. I've actually got it. It's a good one. Okay, so that was a lovely description and history lesson of how you got to the point of Elixir being suitable. So as I understand it, and I hope you can explain, there's 5 elements to the machine learning Elixir ecosystem. And that would be NX, Scholar, Explorer, Axon, and Bumblebee. Could you take us through that or, confirm I understand that correctly?
Yeah, perfect. So I think there are 2 building blocks. One, it's NX. And NX stands for numerical elixir. And what it does is that the main abstractions there is something that we call a tensor. So a tensor is a multi-dimensional data structure. As programmers, we are familiar with lists or vectors, and those are one-dimensional, right? We're also familiar with matrices, right, which are 2D, right? So you have 2 dimensions in there. And then, so a tensor can represent things that are 1 dimension, they are 2-dimensional. They can also represent things that are 3 or 4 dimensions. So for example, something that is 3-dimensional for a computer, it's an image because you have the height, you have the width, and then images, they have like the RGB layers, right? The red, green, and blue layers. Each of them get like a byte to represent, depending on the image format, right? But they get a byte to represent how much red is there, how much green is there, how much blue is there. You have some other images which are like RGBA. But yeah, so you have 3 dimensions, right? You have width, you have height, and then you have another dimension, which is to have like the channels, right? RGB or RGBA and so on. So that's 3-dimensional. A video is going to have another dimension on that because you can think of a video, so it's going to be 4D because you can think of a video to be a batch of images, right? So tensors allow us to represent that, right? To represent all of those things. And depending on what you want to do, so even if you're thinking simply about it, like, well, if I have an image, how do you rotate an image, right? Or how do I rotate a video? How do I convert a video to black and white, right? If you think about all those things, we can express those as transformations on top of this tensor. And NX provides a bunch of low-level primitives, not really low-level, bindings to low-level primitives to do this operation, right? To do all those things. So we can multiply matrices, we can invert, we can add layers, remove layers. There are a bunch of things that you can do, and NX does it. NX does a lot more. So if somebody's listening to this episode, they're coming from Python. NX can also, we have this idea of like serving tensors. We have this idea of numerical definitions. We talk all about that in the project README. But in a nutshell, that's what the NX does. It defines those tensors.
So that's the lowest level.
Yes, that's almost everything builds on top of that. So for example, one of the things that build on top of that is a project called Scholar. So now when we talk about machine learning, a lot of people, they think about neural networks, right? Or deep learning. That's what people are thinking about. So we have a library for that called Axon, but we also have a library called Scholar, which is more about the traditional machine learning. And there we have like algorithms, like for example, clustering. Like imagine you have some data, right? And you can distribute this data in a space and you can say, hey, can I break this data into cluster, find things that are related to each other? Or imagine that you have some points you want to do, like you want to find a polynomial curve that is going to fit those points as close as possible, or you can do a linear regression. So Scholar is a traditional machine learning library. That's what it has in there. And it's built on top of NX. And the other cool thing about NX is that all the code that you write, you can run it either, all the code can be compiled just in time to run on your CPU, and that can make it like much, much faster. Or if you have a GPU, you can also compile that code to run on the GPU as well. So everything that I'm saying about Scholar, it means that it can run on the CPU or on the GPU as well. And then Axon is also about machine learning, but it's about deep learning in particular. So it's about the abstractions for building neural networks. So neural networks, we break them into, they have a bunch of layers. Each layer has like different capabilities. It adds different features. So you need a whole library to define those layers. If you want to train a neural network, you need to figure out how you're going to train the neural network as well. And Axon is a library that takes care of that. So it's the building blocks for building a neural network. If you think about a neural network as a bunch of layers stacked on top of each other, Axon is going to define those layers, and all you have to do is to connect those layers together. And that's going to give us deep learning and neural networks in Elixir. And it's built, again, on top of NX. And then Bumblebee comes on top of that. And what Bumblebee has is that, well, we have a bunch of predefined existing neural networks today, right? And some they're like very popular, right? Like some we often call them architectures. So like GPT is very familiar because of ChatGPT. We have Stable Diffusion. We have Whisper, which is for speech to text. There are a bunch of existing architectures, existing neural networks. And often what people do is that because the most expensive thing is training a neural network, it needs a really large amount of data. And sometimes people, they spend like hundreds of thousands of dollars to train a neural network. And there are people who train those neural networks and they make the result of the training, which we call are the model weights. They make it open source. They make it available. Maybe not open source, the best way to describe it, but it's available and you can download it and you can use it. So for example, well, maybe it's a good time to say this. So if you are excited about trying those things out, you can install Livebook on your machine. We have this thing called smart cells that we can go back and talk about them. But you start a new notebook, you click on the smart cell button and you say, hey, I want to have a neural network. You click that button as well, say, I want a speech to text neural network. And it's going to configure the neural network for you. So you can start running a speech to text neural network with Elixir on your computer and give it a try. And again, this happens because we have implemented those models in Elixir. And because somebody trained this neural network, made the model weights available, and we download it to your machine. And now you can run that thing. And I can say, hello, darkness, my old friend. And it's going to give me the text back. Hello, darkness, my old friend, and everything else. And this part where we build existing models and we can download the weights of the model to your machine so you can run it, that's the Bumblebee project, right? And that's built on top of Axon. So to sum up so far, we have an X, which is the building block. And then we have a Scholar, which is all about traditional machine learning. And then we have Axon, which is about deep learning, about neural networks. And Bumblebees gets the framework, right? So if you're coming from web, you can think like, get Phoenix or Rails or in Django, right? Like imagine that you have a web framework that's going to be Axon. But imagine that we had a bunch of like ready web applications all developed for you to try out and run them. And that would be Bumblebee. It's basically a bunch of existing models that they already work. They have the parameters. You can just get them, try out, deploy to production, and start running them. Those cover 4 of this. I'm going to use this opportunity to have a break before I go forward.
I'm going to go through an example and pull apart and summarize everything we've just talked about because there's a lot of new terms there. So NX is the fundamental different types of data structures that we need to get the data we're analyzing into some type of format that fits NX. That's the bottom layer. Scholar is our traditional machine learning. So I would understand that to be, you need to know what you're looking for, whether it's polynomial or linear, or the other terms you said. So you need to know what you're looking for in order to use that. Axon, you nicely explained, is the framework that you're using, which brings you into neural networks or deep learning, which we'll need to take a step back and define the difference between, or the complementary parts of machine learning and neural networks. And then Bumblebee is kind of the nice go and grab this existing model or algorithm from somewhere like Hugging Bear that hosts these types of things, download it and apply that to our data set or the data we're interested in. Is that about right?
Yeah, just with the correction, Huggingface.
Huggingface. I put Hugging Bear in here.
Yeah. No, it would also be a great name, Hugging Bear. But yeah, it's Huggingface. And for those who are not familiar, I like to say, I don't know if they like the description, but I like to say it's the GitHub for machine learning and for AI and neural networks. So all the models are there with the parameters and you can deploy and run and give things a try. I really enjoy everything that they have been contributing to the machine learning ecosystem.
And a neural network, is that a bunch of computers? Or how do we define that?
So it doesn't have to be a bunch of computers. So a neural network, it's a model. And I think, I'm not sure exactly how I would say what exactly is a neural network, but it's a machine learning model. And I think if it has like some specific layers, that would describe them as a neural network, but I'm not sure like what is the essential bit of everything that a neural network has that makes it a neural network. Like, so for example, in Scholar, we have models. Why those things are not neural network? I'm not 100% sure what is the thing that makes it different.
Okay, I get the feeling that's going to be another show. It's going into deep learning and neural networks.
Yeah, Sean would definitely be ready to answer.
Yeah, I think we could do a deep dive show on that.
There is one, I think, just as a parenthesis here, I think one of the cool things about the neural networks is that you define the layers that compose of the neural network. And it uses, because a neural network has two parts, right? We say it's the training part where you have to train the neural network. And I said that's expensive. And there's the inference part that after it's trained, you say, hey, convert this speech to text, or tell me if there is a dog or a horse in this picture, right? That's the inference thing. And again, I don't know if this is what makes a neural network, but one of the interesting things is that the training, the code is derived from how you stack the layers together. You don't have to say, here's how I train it. You just assemble the layers together. And then we use mathematical properties to derive how we are going to train the neural network. And maybe that's what makes a neural network an actual neural network, but I'm not sure.
Okay, that's cool. We did a show actually in February, episode 249 with William Falcon on optimizing deep learning models. And that goes in depth into PyTorch and PyTorch Lightning and things that you mentioned. So I'll reference that for the listeners. Okay, let's try, if we can, in the last 10 minutes or so, to come up with an example that uses everything. So my interest at the moment is fraud detection, whether that is in telecoms world or, API abuse or a bank transaction that's fraud. Would you be able to take us through, if possible, where you start with that? You've got a bunch of API logs or events or call data records or phone calls. That would be your raw data that you've kind of got to find a model for, get into shape. How does all that work?
I have no idea.
Good answer.
Yeah, as I said, I am working on an X, and sometimes Sean is like, hey, this neural network is slow or it doesn't compile. I don't know what it does. I don't understand it, but it gives me a way to reproduce it, like that I can run it on my machine. I don't actually need to care about what it does and how it's stitched together. I can go there and I can optimize it. I can figure out ways of making, it efficient and improve it and even help come up with the abstractions. But when it comes to using them to solve the problems, I don't know.
What about Bumblebee? When we go and get a model, what are we actually running that against or on your data?
What do you mean?
When you're downloading this model that fits your use case, are you inputting a bunch of CSV records or, when you're using Livebook?
Yeah, so going back to the ecosystem, right? You said there were 5, and there is one that I did not cover, which is Explorer.
That's right, yeah.
Yeah, that's the 5th one. So everything we have talking about, NX, Bumblebee, Axon, Scholar, those things, when we think about tensors, they are all zeros and ones. They can only represent numbers in them, right? And so it doesn't really know about words. Right, so you may say, okay, so how can I do spam detection or how can I do speech to text if the thing doesn't know about words? And so, for example, we have something before, which is called a tokenizer. And what it does is that it goes through the text, for example. You also have to train, but it goes through the text and say, hey, this token here is going to get the number 1. This other token is, so if you get hello, it says the hell thing, maybe, or ha is going to get the number 1, low gets the number 2, and you split everything in tokens, space is a token, and you give the numbers, right? But that's not all. That's not all the data that we have. Not only strings, we also have datetimes, right? Which maybe we can treat them as numbers, but maybe they encode different properties in there that can be interesting. Maybe the interesting thing of a datetime is not really the date part, but the time, depending on what you want to do, right? So for example, maybe fraud detection is more common at midnight, right? So it doesn't matter the date. It matters that, that it's midnight, right? So data is richer, right? It's not only zeros and ones. And we need to be able to get this data from a CSV file, from your database somewhere. You need to be able to get this data and to message it, right? To transform it. So eventually we can transform it enough that it becomes zeros and ones in a way that we can feed into those tensors, right? So that's what the Explorer project does, right? So if you're thinking about, so let's try to put everything together. So Explorer is, you can think about it as an Excel or as a table, a database table, right? It's columns that have a type and a bunch of rows, and you want to process those columns in a very efficient way as fast as you can, right? Because a lot of the issues with machine learning, it's about like massaging the data. So if you're using Livebook, your workflow would be something like, well, I'm going to open up Livebook. I'm going to bring the CSV into Livebook, and I'm going to use Explorer to parse that CSV into a meaningful data structure. And then from there, a data engineer or a data scientist is going to try to explore a little bit the data, try to understand some parts. Maybe the data is dirty. Maybe, like sometimes the numbers are less, the names, maybe the name is important. Sometimes the names are last name, comma, first name. Sometimes it's first name, last name. Maybe the dates, they're not necessarily correct. Sometimes with time zones, sometimes without. You may want to do a lot of messaging on that data. And then eventually, after you message that data, it's in a state it's good. Maybe there's an existing machine learning model that you can try. And that existing machine learning model would be trained on data of some sort. Say, look, the person who trained that machine learning model massaged the data in this way, and then you massage the same way, give it to the machine learning model, and the machine learning model is going to tell you if it's fraud or not. Or maybe you need to get an existing model, you have to train it. And then if you have to train, you get all of your data, for example. So you need somebody to go through this data and say, hey, this was fraud, this was not fraud. You need to label the data. And then you define this data that you're going to use to train and test the model. And then there are a bunch of techniques of things that you can do here. But then what you do is that if you know what is fraud, what is not, you use that to train the model. You use that to test the model to see if the model is accurate, because you may not want to have false negatives or false positives. And after you go through this whole process, several tries, most likely, the hope is that you're going to arrive to a model that are going to be happy to run in production. And our tools are going to help with that part as well, and give a bunch of options on how you want to deploy those models, how you want to scale it in the same machine, different machines, one GPU, multiple GPUs, and so on. That's kind of the general overview of the problem.
I'm trying not to laugh here, because for someone that just said they had no idea, that was a perfect explanation of how it all works. Because that's how I had it in my head, and you explained it perfectly. So thank you. So just to summarize, Explorer pulls apart the data you're interested, depending on your business logic and your skill set as a data scientist or whatever, you're trying to pull apart what's important from that data to you and why. And then you get it into the shape and form to either run against existing models or create your own, which ends up in NX in a GPU or a CPU.
Yeah, you asked me to paint Mona Lisa, and what I said is that it has a mouth, eyes, nose.
Yeah, that's fine.
The rest is up to you.
Do you have any idea of how you build a model versus an off-the-shelf one from Hugging Face? Is that something this can help you with, the machine learning ecosystem in Elixir?
Yeah, so usually you build a model, you would get Axon, which has the layers. And the models, they would say, like for image recognition, it's going to be something, you're going to have a dense layer, and then you have like a convolution layer, and then you would stack the layers together. That's part one of like defining a model. It will be like sticking those layers together, right? But then you have to train it, right? Which is the tricky part. And that's going to give you the model weights that you would be able to run in production as well. One of the things that is also worth saying for people who are not familiar with machine learning is that you can also like fine tune. So for example, you can get like a general model for like fraud detection, but then it may not be like super accurate on your data, but it may be more efficient, both in terms of costs or even more accurate for you to get, instead of training everything from scratch, for you to tune that model on your data. So you don't need as much data as before if you're just going to fine tune something that exists. And that's also an option. But yeah, like I assume like most people, they're not necessarily. So let me try to recap. So it's 3 parts, right? So one part is like, what layers do you have and how you're going to stack those layers together. That's one part of the problem, which is basically done by research. Like researchers around the world, they are like working on those things, thinking about new layers and how to stack them. But after somebody publishes a paper like how to do image recognition, how to do fraud detection, right? They say how the layers should be stacked together, and you use Axon to stack those layers together. Right? And then somebody has to train to get the parameters.
And do the labeling.
Yeah, labeling is part of the training data. And then after you have all those things, you can give it an input, like some data that you got from CSV or some text if you're doing spam detection. So you're going to have your input and you're going to have your output, which can also be different kinds, right? It can be a Boolean thing. Oh, this is a spam, this is not a spam. But if you're doing image recognition, or image classification, right? It's a dog, it's a cat. You may have all different kinds of things that it's going to say. And the interesting thing is that it doesn't necessarily say it's a dog or a cat, for example, or a horse or a hot dog, right? It just says, well, I am like 60% sure it's a dog, 10% sure it's a cat, like 1% sure it's a hot dog, right? And it just gives you the percentage. It's going to be one of those. And then you have to decide if that's good enough, right? Or if it's ambiguous and you don't want to make a decision and so on.
I suppose that'd be like your example before, where if it's a poorly trained model, you might show a picture of a lady and it says, yeah, I'm 60% sure this is the Mona Lisa. But as you fine tune it and say, you need to be looking for this, this, and this, it would find it.
Yeah, that could be one of the things. So again, my understanding, I'm not 100% sure, is that, so for example, imagine that you have a very specific use, like you want to identify different breeds of dog, or imagine that you work with tooling, like very specific tooling, where, like maybe where you're working, for us, if we see like 3 different kinds of hammer, I would say it's a hammer, right? But depending on what you're working, like, no, this is a hammer with the square head that I use for this. This is a hammer for this and this, right? Some people may have like specific uses. You get an existing model that already does the image recognition, and then you fine tune it to teach you about like the specializations. That's one way to go about it.
Yeah, I think that's called assisted learning, isn't it?
I'm not sure because there are like so many terms related to that. I've heard like transfer learning. I know there is fine tuning. I know there's like the reinforcement learning, which is something else. But there are so many terms that I'm not exactly sure what makes one or the other, like what are the differences between them.
It reminds me of when Spam Assassin first came out. And as a system administrator, I used to spend tons of time dumping folders of spam into Spam Assassin and training it again. You had to constantly keep feeding the new changes. Okay, I think that's us pretty much at the end of the show.
Yeah, just one thing, because a thought that came because you mentioned spam. I think it's worth like also mentioning that the spam filters, they got like really popular before like deep learning became a thing, right? Which I think points back to Scholar, right? Like the way that people were doing spam filtering, I believe, before deep learning is that they were using tools like Scholar. They were using traditional machine learning tools. And one of the advantages of that is that usually they are much cheaper to run. They don't require that many resources. So it's something that, depending on what you're doing, like maybe you should consider, traditional machine learning is fine. I don't need the deep learning one. And it's something worth thinking about.
Yeah, thank you. So what's next for you in the machine learning world? What are you currently staying up late doing or, looking forward to doing in the morning?
Yeah, so this is something that I want to announce. I want to publish within the next month. I think like for when we started this machine learning stuff, which was about 3 years and a half ago, like I had a huge list of things to do, like really massive list of things to do and learn and explore, because you are at that point in your journey that you need to know what to do and what not to do. Like you say, like, look, it's not worth investing time in this particular area. This is where we should focus on. And like I had a huge list, and we are at a point where like we still have a lot of work to do, of course, but the core of the things in the list, it's all tackled. So now we will continue to focus on like improving what is there, adding new capabilities, rather than, like adding a new foundation, like a block like we said, there are like 5 blocks. They're not necessarily thinking about the 6th or the 7th block. The blocks, they're in place, and now it's about continue to improve them. And that's pretty much our plan. We just continue improving, adding more features to NX or to Bumblebee, implementing more models. And as companies and teams, they are starting to run those things in production, I'm sure we're going to get more and more feedback that we are going to take and continue to improve in the tooling. So I'm really excited and proud that we are getting out of this like discovery loop and now get into like this cycle where we continue improving rather than starting new foundations all the time.
Thank you. I think we did a great job of covering why anyone should invest time in the Elixir world for their next machine learning project. But if there was one thing you'd like a software engineer to remember from our show, what would you like it to be?
Yeah, no, that's a good question. I'll have to think about it.
Was there anything that we missed, that we forgot to mention?
I think through the description, hopefully folks got the idea of all the exciting things that you can do with Elixir, right? Like you can, as I was saying, you can start Livebook and you can start running a machine learning model. And from Livebook, you can kind of build a chat app where you can send audio and it's going to convert that to text. You can send an image, it's going to classify that image, it's going to generate text. There are all those crazy things that you can do and have those things interact with your Elixir code base in all interesting ways, plot graphs, transform data. So that's kind of like, that's where I want to think like, what Elixir is for today. I'm thinking like, well, I want it to be this tool where you can kind of throw any problem at it and you're going to have a great time like tackling that problem, and we are going to have good abstractions for solving that problem. That's where I hope we are going towards.
Thanks. Well, for me, I'm going to have a go of what people should remember from the show. And this is how I think of it. Elixir is not just a programming language, it's a whole ecosystem. I think that's where it's got to today over the past 10 years. I think people just think of it as a programming language, but when you're actually using it day to day and you've got the whole tool chain, ecosystem, places to reach out, communities to join, it's not just a programming language. So where can people contact you or, reach out to Chief Adoption Officer? I just love that. Where can they reach out to you?
Yeah, so best places. So if it's something like regarding, let's say, I don't want to say enterprise, but if it's something related with business, company, go to dashbit.co, our website, and you can reach out to me there. We are a very small company. That's why I didn't want to call like CEO, because I always find it funny when it's like, oh, I'm the CEO of a 3-person company. And I was like, I don't want to call myself a CTO because like we're not really running any technology. Like we do open source, right? So I thought like, oh, Chief Adoption Officer, or I was thinking like Chief Open Source Officer, but that like doesn't make a lot of sense. So I was like Chief Adoption Officer. But yeah, it can be there. But otherwise, you can reach out to me through the Elixir forum or through GitHub. That's where I am most active.
Well, thank you for coming on the show. It's been a real pleasure. This is Gavin Henry for Software Engineering Radio. Thank you for listening.
Thanks for having me.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.